You're going to need that sheet that I just passed out to you eventually when we're doing the lecture today. It's what I call the periodic trend help sheet. Okay, so this is a help sheet where you have everything in the same area where you can see it and get to very quickly when you need to use this. So we've talked a few things about the periodic table, and you might as well take your periodic tables out now. We're going to be using them throughout the day. We've talked a little bit about them, such as metals, nonmetals, metalloids. We talked about the S block, the P block, the D block, the F block. So we are going to go on into certain properties of elements. And remember, this is one of the key things that Mendeleev used when he set up the periodic table. He said, these elements have similar properties, so I'm going to group them together. So we're going to talk about these properties and patterns that exist. So, periodic trends. Now, just to say a little bit about this slide and note-taking skills, okay? If you go through and look at this, periodic trends, there are several important atomic characteristics that show predictable trends that you should know. Now, do you think that's essential to write down? No, okay? The first and most important is atomic radius. What I would write about that is atomic radius, and then I would write it's the distance from the center of the nucleus to the edge of the electron cloud. So I would have on this, under periodic trends, the atomic radius is the distance from the center of the nucleus to the edge of the electron cloud. That is the juice, so to speak, of this slide. The other stuff is just flow. It is flow. So it's going to be important. It might not be terribly important, but it's good to start taking or getting some note-taking skills where we're not copying everything word for word. Now, the atomic radius. Since the edge of the electron cloud is difficult to define, we use the covalent radius, which is the distance between the nuclei of two bonded atoms. Okay? It's a little easier for us to find the nuclei of two bonded atoms than the edge of the cloud. So they take the radius between those two different nuclei. Okay? It's usually measured in picometers or angstroms. So if you see the little a, that looks to me like a little 0 or a degree sign on top of that. That is an angstrom. It is equal to 1 times 10 to the minus 10 meters. So it's a very, very small number, which we would expect that number to be small if you're measuring distances in between atoms. Yeah, it's going to be teeny. So here's just an example of a covalent radius and how they determined it. Okay? We look, here's two bromine atoms bonded together. So that's a molecule of bromine. They take the nucleus of one and measure the nucleus of the other, and they get 2.86 angstroms. Take half of that to get your atomic radius, because that is the covalent radius. So they use that number for the atomic radii. The trend for the atomic radius in a vertical column. What was vertical? Up and down, right? So we're talking the different groups, okay? For instance, the alkali metals. We talked about those yesterday, the group 1 elements, okay? Up and down, vertical, okay? The column, the atomic radius in a vertical column, the smaller ones are at the top, the larger ones are at the bottom of the family. Now let's think about this. Why? Why are the larger atomic radii at the bottom of the column? They have more protons, nor more neutrons, therefore they have more what else? Electrons. They have more of everything. We have more shells, don't we? We talked about, the different periods, the electron configurations. They're just flat out bigger on the bottom than they are on the top, right? Okay? So, the reason is that there are more principal energy levels, just like I stated there. There's more stuff down at the bottom than there is at the top of the family. Now let's look across a periodic table, across the period, the horizontal way. It is less obvious. Okay? However, as we go from left to right across the period, each hop we make from one element to the next, we are adding protons, we're adding electrons, we're adding neutrons. Electrons are added to existing principal energy levels and existing sublevels. So as we're going from left to right across your periodic table, each element we're adding a proton and electron, and could be anywhere from 1 to 2 neutrons. The effect is that as we are getting more positive, it is pulling on the electron cloud, because those electrons are negative. So as the nucleus is more positive, the electron cloud is more negative. The increased attraction pulls the cloud tighter, making the atoms smaller as we move from left to right across the period. Now, with this, it kind of gets, if you're thinking common sense, you would think you're adding more and it's getting bigger. Okay? Doesn't common sense tell you that? You add more, you get bigger. But the thing is with this is you're adding more charges that attract each other. So as they're attracting each other, as you're getting more and more, that charge pulls them closer together because opposites attract. Opposites attract. So those protons, as we're getting more and more protons, are pulling the electrons closer, so the atomic radius is going to decrease as you go left to right across that periodic table. That leads us to something that we call the effective nuclear charge. Now, I told you that these protons were pulling in these electrons because the opposites are attracting. Okay? The effective nuclear charge is simply a name we give to that pull. Okay, it keeps those electrons orbiting that nucleus and not falling off into space somewhere. Okay, if we would go to the planetary model, what would the effective nuclear charge be like if we're talking about planets? What keeps our planets around the sun? Gravity. Okay, so this effective nuclear charge is like the gravity of the atom. It keeps those electrons there. The closer electron is to the nucleus, the more it's pulled in. So as the effective nuclear charge increases, the pull of those electrons are tighter and tighter, closer and closer. Therefore, the overall trend will look like this. Now, this doesn't tell you a whole lot. That doesn't help you a whole lot. This is something that I just got off of Web Elements, which is a good place to look up stuff on elements if you ever need to. webelements.com. Okay? But, you know, they have big, you know, here and little. But the general trend is what I'm more concerned about. So you have a chart, and you have a help sheet, and your help sheet has a place for the atomic radius, and it looks something like this, only it is in black and white, not color. So when I'm looking at the atomic radius of my help chart, okay, down, okay, as they go down, they are increasing. As they go across the period, they are decreasing. So what should be the element that has the greatest atomic radii? Francium, because it is right down here. Okay? At times, what I like to do is I say, okay, if I'm thinking of atomic radii, I'm thinking of francium. Because I know that it's the biggest, I can figure out then where my arrows should go. So an overall trend on the periodic table is that as we go down and to the left, the atomic radii are getting bigger. Okay, so something just to note, that my arrows up there are pointing to where we have the biggest atomic radii, where the biggest atomic radii occurs. Now we're going to talk something about shielding. All shielding is that when we have more energy levels added on, the inside levels shield the outside levels from the nucleus. So, the effective nuclear charge on the outer electrons are less than on the inner electrons. That's just saying that the pull, okay, the pull of the nucleus, okay, the effective nuclear charge, that pull is less for the ones that are further and further out than it is for the ones that are closer. Makes sense, doesn't it? You would think that the pull of gravity of the sun would be greatest on Mercury, right? Because it holds it closer, and be less on the planets out further. Well, that's all it's saying here. The electrons closer are held tighter than the further away electrons based on the shielding. Okay? This is going to make sense when we sit there and talk about bonding later on. Okay? Bonding later on in the course. Ionization energy. If an electron has enough energy, it can overcome the effective nuclear charge. It can overcome that force holding it on to that particular nucleus. Well, how does it get enough energy? In the form of a photon. Okay? We're not going to go real deep into that, but it can get enough energy to completely leave that particular atom. Now let's talk about this. We've discussed that these atoms now, we're having equal amounts of protons and electrons, right? If I lose an electron off of that atom, I now have more pluses than I do minuses, don't I? That is something that we call charge. It has a charge. In this case, it would have a positive charge because there's more pluses than there are minuses. If it has a charge, it has become ionized. It has become ionized. The amount of energy that is required to remove an electron is called the ionization energy. It's measured in kilojoules. The larger the atom is, the easier its electrons are to remove. Okay, most likely due to the shielding. Those inner layer electrons are protecting the outer layer ones, so they have less pull of the effective nuclear charge. Ionization energy and atomic radius are inversely proportional. Ionization energy is always endothermic. That is, energy is added to the atom to remove the electron. Add energy to the atom to remove the electron. Once again, here's our Webb element things. And notice, over here in the nonmetals, this is where that's really, really, really big. Okay? Really, really, really big. It takes a lot of energy to remove those electrons. The reason being, they're getting closer and closer and closer to filling their electron shell. Okay? They're getting closer and closer to filling that energy level, so they want to keep those electrons. Notice these ones are really, really small over here. Okay? These are the ones that only have 1 or 2 electrons on that outer energy level, and they tend to want to get rid of them fairly easily. So that is kind of a trend that we'll talk about more when we talk about ionic bonding. So on your help sheet, ionization energy, okay, increases as we go up. Remember we said that the bigger the element, it's easier to remove the electrons. So the smaller will hold those a little bit tighter. So as we go up, the ionization energy increases. As we move from left to right, the ionization energy increases. The nonmetals do not want to lose their electrons. The metals, they're okay with it. Nonmetals, no. Metals, yes. So if we look in terms of losing electrons in this ionization energy, it's going to take the most energy to take an electron from what element? From what element? One would think that, but let's not count the noble gases, because the noble gases will not lose electrons. Okay? Fluorine would be the one that I would think of, but those noble gases have really, really high ionization energies because they have full outermost shells. They're filled. So they absolutely do not want to lose them. Okay? So my help sheet, you should draw in as so. Electron affinity. The electron affinity. What is affinity? Okay. Electron affinity is the energy change that occurs when an atom gains an electron. When an atom gains an electron. So the electron affinity, it's also measured in kilojoules. When we said ionization energy, we said it's endothermic. Well, electron affinity is usually exothermic. It's not always, but it is usually exothermic. So the electron affinity is the energy change that occurs when an atom will gain an electron. Now, I said that this electron affinity is usually exothermic, but not always. Well, here's why. Okay, the electron affinity is exothermic if there are empty or partially empty orbitals for the electrons to occupy. So look up on the board here. Just so happens that I drew this up there yesterday. Okay. Are there any empty or partially empty orbitals there? Well, yeah. I see here's a 3px, here's a 3py, here's a 3pz. I only have 2 electrons on those, so there's plenty of spaces to add electrons. The place where it's endothermic is if we don't have those. Okay? Let's say we filled an s orbital. So we have, 2s2. We filled that s orbital. We have to add a new orbital to get more electrons on there. That's where it's going to be endothermic. Okay, that's where that process will be endothermic if there's no room or orbitals to add electrons to. So when we have our help sheet on electron affinity, it should look as so. As we go up a group, it increases. As we move across from left to right of the period, it increases. Okay? So, who will have the greatest electron affinity? Who wants to attract the most electrons? Once again, let's not talk about noble gases because they're already filled. They're different, guys. Fluorine wants to attract the electrons the greatest. Remember, helium's already filled. He doesn't care if he gets a new electron or not. He just doesn't want to lose any of them. Same thing with argon. Already filled. Doesn't want to lose them. Okay? Fluorine, however, wants to grab some. Wants to grab one. The metallic character. The metallic character is simply a measure of how easily atoms will lose or give up electrons. How easy atoms will lose or give up electrons. Now let's think about this. Okay? Let's think about this. Based on our discussions that we've had already, who wants to lose electrons? Where on the periodic table would you think electrons want to be lost? Right side, left side? Left side, right? The left side, because those shells are less filled. So the left side of the table, the more metallic. Remember, we said that the alkali metals were very, very reactive. This is the reason, okay? This is the reason. So the metallic character, the atoms that want to lose or give up electrons are on the left side of the periodic table. So, based on that, our metallic character increases as we go down a group. So they want to lose electrons more and more as we go down the group. Okay? As we go from the non-metal side to the metal side, they want to lose more electrons. So what element will have the highest metallic character? Francium. Francium. Electronegativity. Let's talk about the electronegativity. Okay? We'll use electronegativity throughout the year a lot. Okay, we'll use this a lot. It is a measure of an atom's attraction for another atom's electrons. It's an arbitrary scale that goes from 1 to 4. We call the units for the electronegativity as Paulings. Okay? Paulings, probably the gentleman who created the electronegativity scale. Okay? Generally, metals want to lose electrons. They are electron givers. Okay? So their ability to attract another atom's electrons are going to be small because they don't want to attract electrons. Who wants to attract electrons? Nonmetals. Okay, look at your periodic table. Okay, look at the halogens. They're one step away from filling their outer shell. Because remember, the filled shells are where the noble gases are. So they're one step away from filling them. Do you think they want to attract electrons? Yeah. Then they'll be filled. Okay? So metals generally have low electronegativities. Nonmetals generally have high electronegativities. They want to add electrons. What about noble gases? What do you think about noble gases? Rachel? Right. Do they want to attract electrons? So would you think their electronegativity would be big? No. No, we wouldn't think so. Because they do not want to attract electrons. So, when we look at our help sheet, here we go. When we look at our help sheet, here we go. So the greater values are where the nonmetals are. The lower values are down towards the bottom left. The higher values are top right. So fluorine will be the element with the greatest electronegativity. Now here's just another part. We said that the noble gases don't want to attract electrons, so their electronegativity is going to be zilch. They don't want any new electrons. Overall reactivity. Overall reactivity. Now, as we talk about overall, okay, we're going to just kind of wrap everything up into one chart on your help sheet. So the overall package. When we do this, we have to treat metals and nonmetals a little bit differently. Okay? We can't just draw arrows, 3 arrows like we have been, because we got to treat them differently. So we're going to put some more arrows on that last one. But in generalization, the most reactive metals are the largest ones because they're the best electron givers. In general, the most reactive nonmetals are the smaller ones because they are the best electron takers. So if I have to make a help sheet with a generalization of overall reactivity based on metals and nonmetals, I create them a little separate. So I say, okay, where is going to be the most reactive metal? Here. So the most reactive metals are going to be there. Now notice, I didn't take my line over into the nonmetals, did I? Okay, I didn't take that line over to the nonmetals because the nonmetals are different. Where's my most reactive nonmetal going to be? No. Yeah. Fluorine. So nonmetals are going to look like that in terms of reactivity. And once again here, how reactive are the noble gases? Not. Don't want a piece of it. They're already happy. They got a full outermost shell. Now we're going to get into a little bit of background terminology. So you're going to see these next few slides are going to be some terminology slides that we're going to talk about. I don't know if this is a good time to do it or not, but we're going to do it anyway. There's no better time than the present, huh? Ever heard that? So we're going to talk about these now. The octet rule. The octet rule. Now, what is oct? Oct is 8. So the octet rule is dealing with an octet or a group of 8 electrons in their valence energy level. Now we'll talk later on, and we've hit it a little bit. Valence is the outermost energy level. Valence is the outermost energy level. Now, most atoms want an octet of 8. I have exceptions up here. Hydrogen, lithium, beryllium. This is an exception. These are exceptions to the octet rule. Why are they exceptions? They are very, very close to helium, right? Look at your periodic table. Beryllium, lithium, hydrogen are all very close to helium. How many electrons does helium need to fill its outermost energy level? 2. Okay? So when these 3 elements gain or lose electrons, they want to go to 2, not to 8. So that is why that they are exceptions to this octet rule. Now, how do elements achieve this octet? By gaining or losing electrons. By gaining or losing electrons. Metals generally want to lose electrons. Nonmetals generally want to gain electrons. And we've talked about ions when we talked about ionization energy. Okay? An ion is just simply something that has gained or lost an electron. Well, let's talk a little bit more about these ions. Okay? Let's talk a little bit more about these ions. More terminology. When an atom gains an electron, it becomes negatively charged. It has more electrons than it does protons. It has more minuses than it does pluses. If that is the case, we call it an anion. An anion. Ones that are positively charged. If I give up an electron, I have more pluses than I do minuses. If I have more pluses than minuses, I'm positively charged. Therefore, I am a cation. Okay? Generalization. Who wants to gain electrons? What elements? The nonmetals want to gain electrons. So the nonmetals generally form anions. Who wants to lose electrons? The metals. So the metals lose electrons. Well, when we lose electrons, we have more pluses. They are positively charged ions. They are cations. Now, a little way to remember these ions, okay? Okay, here's a little way to remember them. Look at her. She's crying. She's sad. She's very negative, okay? This is a little anion. Okay, little anion is negative. So anions are negative. Okay? She's unhappy and negative. Look at this guy. He's a fat cat. Look at those eyes. Those eyes, they're plusy. Okay, so he is a plusy cat. Our cation is a plusy cat. So he is a cation. So cations are pretty positive. All right, ionic radius. This makes sense too, folks, when we talk about an ionic radius. Cations are smaller than the original atom. They lose electrons, therefore, they take an entire principal energy level off, so they get smaller. Anions are larger. They are adding electrons to that outer energy level. So ionic radius, the cations are going to be smaller than original ones. The anions are going to be larger than the original atom. And we're talking about the original atom. We're talking about atom before they have gained or lost the electron. Now, these last two slides, just watch them, okay? Just watch them. Do not write anything down. Just look what's happening. This right here, as you can see, this has 11 protons. What element has 11 protons? That's right, ladies and gentlemen, it's sodium. Okay? Can you see this one little guy right here out by itself? In order to fill the outermost shell, okay, in order to achieve the octet, it's easiest for sodium just to dump that one guy right there, to give it away. Okay, so when he gives away that one valence electron, there we go. There goes the shell. Now is that filled? Absolutely. Therefore, if you count them up, I have 11 pluses. I have 10 minuses. So what's my charge? Positive 1. I have a net charge of 1. So when sodium forms a cation, a positive charge, it's going to be +1. Okay? Now, here is an anion being formed. What has 17 protons? Chlorine is the correct example. Now, if you look on chlorine, its outermost energy level, the outer ring, has 7 electrons, right? How many does it need for an octet? 1 more to get 8. So, chlorine is going to want to add 1 electron. Here he comes. There he is. Now, has chlorine filled the outer level? Absolutely. Now, if you count the electrons, there are 18 electrons. How many protons? 17. So I have a net charge of -1. Folks, I can tell you, this is tough for people to get. The reason being, stop and listen to what I'm saying. I add electrons and become negative. Okay? Everybody, the common misconception, everybody, a lot of people, not everybody, okay? The common misconception is that when we're adding, we're getting positive. When we're adding, we're getting positive. That's not the case, because what are we adding? Negatives. We are adding negatives. So when we add, we get more negative. That's tough for people to comprehend. That's tough for people to get. All right? Now,